Overall, the results are pretty good. Let me remind you of a few things here that are going to be relevant moving forward. First of all, when you're setting up your null and alternative hypothesis, the null hypothesis always has to have the possibility of equality. Less than or equal to, or greater than or equal to. Now, on my stat lab and in the book, they just use equal to. That's fine. I use the less than or equal to and greater than or equal to just out of courtesy to you. They're more user-friendly. The other thing is that you're typically going to be using parameters. So what are your parameters? Parameters are the things we discussed in the video which you recorded just a moment ago before this. Those are these things. They refer to populations. When you're doing hypothesis test, you're testing things about a population. So you should be testing questions about a parameter. Now, as far as testing correlation and linear regression, your correlation test is rho equals 0, and that's equivalent to your linear regression test of beta 1 equals 0. They're the same test. This one was your goodness of fit test. Now, there's a couple different versions of your goodness of fit test on this exam. Here's one down below for problem number 6, in which the probability of winning your null hypothesis is that it's the same for all these, in which case it's okay to do P1 equals P2 equals P3 all the way up to the last one, and they're all 1/10. And that's fine. But if these are different, then you shouldn't be saying that they're all equal. And there was enough people that did that on this first one that said they're all equal. They're not. You should be listing that piece of red is 0.131, piece of orange, etc. So be careful about that when you're doing your null and alternative hypothesis stuff. One of the ones that should be easy to pick out is when you're comparing means for more than 2 populations. There's only one test that we have that allows us to compare means of more than 2 populations, and that's an analysis of variance. So if you see something like that, that should be a slam dunk for you. Linear regression. All right, we did a lot with linear regressions. Let's talk about R first of all. And R talks about the strength of a linear relationship. What does a value of R equal 1 say to you or suggest to you?
Strong relationship.
Not just strong, but a perfect linear relationship, right? It's saying that the data are exactly on a positively sloped line. Or with -1, the data are on a negatively sloped line. They're perfectly on that negatively sloped line. Is there anything that looks like it's perfectly on a positive or negative slope line? No. And how about 0.999? I mean, that's ridiculously close to 1, so you would expect something that's almost a perfect linear relationship there, and it's not there. So if you were being clever about your approach here, you'd say, all right, well, it's not going to be any of these. It just can't be any of those, right? Because you don't have a perfect linear relationship or a near perfect linear relationship or a negative linear relationship that's perfect. So we got rid of all those 3 in orange. So it leaves you with some other ones. Now of those values that are left, let's take a look at this one. This is pretty close to, you know, a perfect relationship. It's not great, but it's close. So let's take a look at your choices. Now it has to be something that's negative, right? So it's either negative 0.4 or negative 0.5. Which one does it have to be? Yeah, negative 0.95. It's closest to negative 1. So, all right, that one's negative 0.95. Where's our other negative linear relationship? Well, there's only one other negative value here. That's negative 0.4. That has to go here. So once we have that one, we got that one. Now that leaves 3 values left, our positive values and 0. So our positive value was 0.7, and we also had a 0.5. Which of these looks closer to a line? The data here or the data here? Bottom or top? Bottom was closer to a line, so that's going to have the higher value of R. You can have a value of R of 0.7. So once you strike that off, it leaves 0.5. That's your only other positive value. And then striking everything off, the only thing that we haven't used is a 0. So that last one has to be a 0, which looks random, which is what you would expect for zero correlation. I'm not sure it's because I gave you a handout that didn't include this, but I thought I was pretty clear about you should know these 5 things. This did not go well for you guys on this exam. I don't know what happened there, but whatever. Okay, let's move on to linear regressions here. So you had a linear regression comparing the old MPG to the new MPG, and if you have a significant regression, you're going to use the regression equation. If you don't have a significant regression, what are you going to use instead of the regression equation?
Y bar.
If your regression is not significant, you're going to use y hat equals y bar. But our regression was significant, so we should write down the regression equation and then substitute in the 22 for x. So there's your 22, substitute it in, bam. Get a quick 19.7, that's your predicted value. Now what is the slope of this line saying? What is the slope in this line anyways? Where is the slope for this regression equation? The 0.85. So every time you increase the value of x by 1, the value of y goes up by 0.85. And in words that relate to the problem, for each increase of 1 mile per gallon in the old system, the MPG in the new system increases by 0.85. That's what I was looking for part B here. For part C, I actually had to add on a little bit. What I was expecting you to do for part C is take a look at the scatter plot. If you want to see if there's evidence to suggest that there's a linear relationship, hey, just look at the scatter plot, right? So that'd be like these examples here. The scatter plot can give you an indication of whether or not you think that there's a linear relationship. But I wasn't complete enough in my answer. Looking at some of your exams, I realized, oh, you could also look at the value of R, which is in the output for your linear regression. That's literally what the value of R represents, is the strength of a linear relationship. It's between -1 and 1. Now, as far as your predicted value is concerned, if your regression isn't significant, then y hat equals y bar. Done. I hope you know the difference between climate and weather. Again, that's not one that went over too well. Do you remember in class when we talked about that one nurse who was murdering people to try and impress her boyfriend? And I said, can that table of values we have be used to convict her? It was a big question. We spent a little bit of time on it. What was the answer to that question? Could the values be used to predict her, convict her or not? No. And the reason was because these tables show an association, they don't show causation. So they could show that, I think it was Kristen Gilbert was her name, could be associated with those extra deaths on her shift, but she didn't necessarily cause them. It just showed association. And by the same fashion, this table can show an association between mortality and owning a dog or not, but it can't show causation. And that was the big point of this problem. There was a lot of other things written, but the one that really mattered was, no, it can only show association. It can't show causation. Value of R squared. The value of R and R squared, you should know what they represent. Here's a nice wordage for the value of R squared, the coefficient of determination. represents the proportion of variability in y that is explained by knowing the value of x. Basically, how good is your model doing? It's not talking about the strength of the linear relationship anymore. That's the value of r. It's just saying, how good is your model doing? Now, the nice thing, if you understand what r squared is, you can look at all kinds of models, not just linear relationships. R squared has to be between 0 and 1. The closer to 1, the better. At 1, you're explaining 100% of the variability in y by knowing the value of x. Last but not least here, the reason I introduced non-parametric tests is because your parametric tests have assumptions that aren't always satisfied. And sometimes it's hard to satisfy those, especially with two hypothesis, or your hypothesis test for two population standard deviations. Both of your distributions have to be normal. And it's just hard to get that. So you should probably be using a non-parametric test. Non-parametric tests are more flexible. They have less assumptions, easier to meet assumptions. Can be used with a wider variety of data. So some of those are some of the advantages of a non-parametric test. Now the downside, and these are different things, it's less powerful and it's less efficient. It wastes information. Think back to the sign test, was which one we did. Sign test, we were throwing out values that had a difference of 0. We weren't looking at the magnitude of the difference. We're just looking at the pluses and minuses. So they're not as efficient. And a definition of efficiency would be how good or how many observations a parametric test requires to be as descriptive or accurate as a non-parametric test. The closer it is to 1, the more efficient your non-parametric test is. It's a ratio. How many values do you need for your non-parametric test compared to how many values you need for your parametric test? The closer that is to 1, the better your test is. So those would be a couple things about efficiency. Any other comments or thoughts about this in general? Nicole?
When am I going to ask you any actual problems about anything that you learned with the non-parametric test?
I don't think on the final exam I'm going to be hitting you up with non-parametric tests, which the only one we really learned was the sign test. But, you know, it wouldn't be a bad idea to, if you know the advantages and disadvantages, why would somebody use a non-parametric test? That's a good question to ask. And what does the efficiency mean? You know, if you had two efficiencies to choose between 0.63 and 0.95, which one are you going to choose? All right, in this case, you want to choose the more efficient test, which would have the higher efficiency. Sam?
Could you show me again your answer for what the coefficient of determination was?
Sure. So, yeah. Certainly, certainly I can't criticize you if you answered something like this on the exam, because it's my exact wording. So, yeah, if you wanted to write that down for the coefficient of determination, that's fine. I'd strongly suggest that you know what R is and what R squared is. Now, one of the things that we did on your regression quiz is I gave you some data and I gave you the value of R, and then you had to figure out, I give you the value of R squared, the coefficient of determination, and ask you the value of R. The big place where people lost points on that one was when they took the square root of R squared to get R, they forgot to also take the negative as well to reflect that you had a negatively sloped set of data. So be careful about that. Good questions. Anything else on this exam? Lisa?
Can you show me H not being alternative for question 11?
So question 11. Now I've got this posted on D2L, or if I don't, I'll certainly post it right after class. But again, one of the things that people got dinged for a point on was that they put P2 equals P3 equals all the way to P6 equals, or they're just all equal. They're not all equal. They have different probabilities, different percentages, and those should be reflected in your null hypothesis. You're giving me a funny look, like.
Because I don't have it with me, That's how I put it. You told me they're not all equal.
They're not. They're not all equal.
But I wrote it how you got it on there.
Did you?
Yeah. I'll bring it tomorrow.
Okay. Well, I must have marked it wrong just because I don't like you.
Maybe it's from that last question.
All right. All right. All right. Good there on this exam. I would definitely be looking this over. One of the things that it provides is, some examples of, random hypothesis tests. One of the things you should expect in your final exam would be stuff like this, where these first 6 problems are asking you basically to set up the null and alternative hypothesis. And I'd like to see you do good on that. There's also examples of that in that exam review that I posted online as well. Towards the bottom, there's a lot of hypothesis tests. And let's just finish up with a couple of them here, just to get rolling. Thank you. Let's look down at this one. Eyewitness accuracy of police. Does stress affect the recallability of police eyewitnesses? This issue was studied in an experiment that tested eyewitness memory a week after a non-stressful interrogation of a cooperative suspect and a stressful interrogation of an uncooperative and belligerent suspect. The number of details recalled a week after the incident were recorded, and the summary statistics are given below. Use a 1% significance level to test a claim that in the article that stress decreases the amount recalled. All right, well, let's think about this for a moment. Now, when you're setting up your null and alternative hypothesis, there's a lot of things you're going to have to consider. So let me kind of zoom out and give myself a little bit more room here. I guess the first thing I would look at would be how many populations. So if there's 3 or more, and you're doing tests of a means, then it's going to be a null hypothesis like this. mu1 equals mu2 equals ... equals mu sub k. There's only one population, there's only one test that we have that can handle something like this. That's your ANOVA. Now if you have 2 populations, then we're going to need to think a little bit more carefully. So 2 samples, then one of several things can happen. First of all, you can test a mean, and that's going to be mu1 equals mu2. But you can test that in a couple different ways. mu1 equals mu2. Why am I separating these? What's the difference between those two? Yeah, well done. Dependent and independent. Independent. Now there's other parameters you can test as well. And keep in mind, you should always be testing parameters. You could test parameters at P1 equals P2. So we got a mean here and a mean here. But then you could have a population proportion. Or there's one other parameter that we could test. Sigma 1 equals sigma 2, which is your standard deviation. That's just if you have 2 populations, 2 samples. You could have 1 sample, which works out pretty easily. You could test a mean, standard deviation, or proportion. So if you're testing a mean, it would look like this. Mu1 equals some mean. We typically denote it with mu sub 0, some specific mean. So this is one population, mu sub 0. Standard deviation, likewise, sigma equals sigma sub 0. And proportion, p equals p sub 0, some specific value. I probably shouldn't put a mu1 there. Maybe it's a little bit misleading. There's a couple tests that don't fit into this scheme very nicely. One of them is your goodness of fit test. That's to see if your data fit the expected value. Does the observed match the expected? So, observed match expected. So if that does, great. If it doesn't, oh well, look for something else. So that's kind of an island unto itself. There's another island unto itself as well. That's also from chapter 11. That was your chi-square test for independence. Test for independence. Those are your tables. And keep in mind that in your test for independence, if you reject the null hypothesis, all you're showing is that there's an association between those two. One does not cause the other. You can't determine that with this kind of data analysis. And there's also correlation, which I could probably squeeze in there, but I'm not going to. So correlation / regression. That's going to be either H0 such that rho equals 0 for your correlation, or H0 such that beta 1 equals 0. So those are your correlation and regression tests. It's the same test. So there you go. So none of these last three kind of fits into neatly into this tree, but those are the different hypothesis tests that we discussed this semester. You're going to have to kind of logically pare your way down. What I would suggest is you look to try and decide which of your parameters you're using, you're testing. You're testing a mean, or you're testing standard deviation. Are you testing a proportion? Are you testing correlation? Try and branch down to where you need to be based on what kind of parameter you're testing. I'll put the copy of this in the scanned in notes for today, but if we want to look at this and apply this to maybe our current example, let's try that. So let's see. Use a 1% significance level to test a claim that stress decreases the amount recalled. Now, they're not overtly telling you what parameter we're using here, are they? So let's see if we can't get it by process of elimination. Are they talking about a correlation here? No, not talking about how one correlates to the other. In fact, technically these would be independent. These are going to be different groups. Are you talking about a proportion? Is this talking about the proportion of people that recalled information? No. You're not talking about variability in any way. So that kind of leaves you with one thing left, and that's mean. Now, how many samples do I have in this problem? 2. So, all right, that branches us down. Here, 2 samples, sample means. Well, wait a minute. Are they dependent or independent? Well, let's look back here. Do these groups have anything to do with each other? So it's independent. So that's the kind of thing that you should be doing with all these examples, is working your way down, trying to figure out, well, what makes sense here. But look at these different branches and try and make sense of this. Have a good mental map of this in your own mind. Comments or questions? Yes?
The second tree with one sample, can you explain what the O's mean right by the,
It just means it's some specific value. It's not necessarily, it's not like two populations. Okay, thank you.